Nuclear fission and fusion. Fission is the breaking apart of a heavy nucleus. It generates energy and neutrons. Fusion is the combining of lighter nuclei. It also generates energy and neutrons. This graphic shows how a neutron bombarding a U-235 nucleus causes a chain reaction where strontium-90 and xenon-143 are generated, and they also generate more neutrons. Here's the balanced equation. If we do an energy calculation, taking the mass of U-235 plus the mass of the neutron minus the mass of strontium-90 plus the mass of xenon-143 plus the mass of 3 neutrons times the speed of light squared, the energy turns out to be 3.3 times 10 to the minus 11 joules per nucleus of U-235. Per mole, it's 2 times 10 to the 13th. Compared to the combustion of a ton of coal, which is 5 times 10 to the 7th, you see that the energy released is much larger for the nuclear reaction. Nuclear fission depends upon having a nuclear chain reaction which is self-sustaining. It is a self-sustaining sequence of nuclear fission reactions. The minimum mass of fissionable material required to generate a self-sustaining nuclear chain reaction is called a critical mass. This diagram shows a chain reaction. Here's a diagram of an atomic bomb. There's a subcritical uranium-235 target which is hit by a subcritical U-235 wedge by the explosion of a chemical that drives it into the target. Once that happens, this is what happens. Here's a diagram of a nuclear power plant. Here on the left, the reactor has nuclear material that is used to heat up water to make steam to drive a steam turbine. This water is then cooled and recirculated. Here's nuclear fission. On the Sun, we have a fusion reactor. The reactions that take place are on the left. We have deuterium reacting with another deuterium isotope, making tritium. Deuterium reacting with tritium to make an alpha particle, and lithium reacting with deuterium to make more alpha particles. In each case, you see the energy released. This is a diagram of a magnetic plasma confinement called a tokamak. It's been used not too successfully to try to create fusion reactions. Let's look at the biological effects of radiation. The radiation absorbed dose, the RAD, is equal to 1 times 10 to the minus 5th joules per gram of material. More importantly is the Rankine equivalent for man, also known as a REM. A REM is a RAD times Q, where Q is a quality factor, depending upon whether it's a gamma ray, a beta particle, or an alpha particle. This table shows the average yearly radiation dose for Americans. Many radioisotopes are used in medicine. Sodium-24, a beta emitter, is for blood flow. Iodine-131, thyroid. Iodine-123 is used in brain imaging. Fluorine-18, positron emission tomography, PET scan. And technetium-99 is an imaging agent. See the graphic, the picture actually of a brain images labeled with I-123. Again, a table showing radioactive isotopes used in medicine and what they're used for. Here are thyroid images labeled with I-125. Patient undergoing a PET scan. This is what it looks like. arthritis imaging with technetium-99. Thallium-201 used for diagnosing of heart disease. It's an incredible looking scanner there. And this is the result of that. These images are actually of a beating heart.